Thank you, Haley. Thank you. Don't do it. Okay. All right. What she has just done in this, well, let's talk about this bit of chemistry here. This is a bit showing some of the chemical reaction between this vitamin C tablet to the water. I put the 100 mils of the water there. So what you see there is it's turning to the kind of blood orange color, as you can see. Okay. In chemistry term, we call this as a solution. This is a solute and solvent. And what we put over here look like this. It's kind of called as a solute. So to make a solution form, we need to generally put some sort of the solute into the solvent to make this kind of solution form. So state-wise, when you put in the solute, we use a solute on the state as a solid or gases. So as you heard some fizzy sound over there, that means that there's a carbon dioxide within that too, which is carbon that comes out in the forms of the gases. It kind of melted into the water, just like your soft drink as well too. You see there's carbon dioxide kind of melted inside of that water too. And the solvent, okay, generally we use water for the solvent many of times, but there are some cases we can't use the water as a solvent. So think about, sometimes we use alcohols, like thinking of the paint. The paints are mixed with a bit of the alcohol because the paints cannot be mixed in the water. Okay, and then they're making solution form in here. So today we're going to talk about a bit more about quantitative analysis chemistry than how we're going to determine something called concentration. So what I do here, I'm going to make another solution of here. Okay, so showing you the second making the second solution there. So I put one tablet each, and you're seeing that it's turning into solution form here as well too. Okay, whilst we're waiting for that, I'm going to put another tablet to the one that Haley made. So I'm making the second solution here. This one has two tablets. This one here has one tablet. Let's see, like, you can kind of expect that it's kind of dissolving everything in there, and the fizzy sounds comes out. Right, just waiting to all get melted. Now, then, by looking at these two solutions here, this one with the one tablet, one with the two tablets here, what can you tell me about the difference between these two? This is a little more darker. So, I mean, it's clear. It's not that clear though, because it's not really showing, but it's actually showing more fizziness, and as we dissolve it more, yes, it's going on to darker red over here. Unlike the kind of pale, like in the kind of pretty pink there, yeah. So that shows that how, in case of here, putting the two solutes into the one same amount of volume here, we call this as a high concentration. And how do you know it's a high concentration? There's many ways. You can see the color, or you can taste it, see like more sugar, more fizziness, more vitamin C, which is not really good. But by looking at what contents we have inside the same volume, we can determine the concentration. So the way we can use the concentration, something we use a cordial too, the unit of concentration we can use, we have these many of the concentration units. So generally we're using the units like this. First, grams per liter, which in the short, grams per liter, like this. So assume this is having approximately, say, 1,000 milligrams, or 100 grams. We had example of the 100 grams of those tablets into 100 milliliter. Okay, how are we going to convert that into gram per liter then? Okay, what we know about 100 milliliter, well, you can write it in the fractional form like this. It's like 100 milliliter in the liter form is known as 0.1 liter, as 1 liter is 1,000 milliliter there. So it's kind of giving you the 1,000 grams on the top. We have fixed the unit. It's showing you what? 1,000 grams per liter in that case. Okay, that's common concentration unit we use in the real day life as well too. The second unit we have, we sometimes use, is the parts per million, ppm. Has anyone heard about ppm? Okay, if you know like some of the forecasts too, again, it's probably popular in the Korea, like, and they're using those to measuring the microdust in the atmosphere, saying that, oh, we have this much ppm too. So what's the ppm stands for? Okay, ppm stands for this. It's same as the milligrams per liter. Okay, let's think about what we mean by milligrams. Haley, what's the milligrams in the grams? 1 grams is, okay, so well, 1 gram is the same as 1,000 milligrams, which is 10 to the power 3 grams there. Then what would be the 1 milligrams into the grams? 10 to the power minus 3 grams then too. Okay, so can we say the milligrams per liter is actually same as 10 to the power minus 3 grams per liter? Or grams per liter as in like grams per liter there? Okay, so let's convert that. We had 100 grams per 100 milliliter, which was same as 1,000 grams per liter there. Then what would be that 1,000 grams in the liter in the ppm? First, think about so let's convert the milligrams per liter. 1,000 grams, as we know, 1 gram is equals to 1,000 milligrams. Okay, so that was actually, this is the same as 10 to the power 3 grams per liter, first of all. Having the what? Grams into changing the grams to the milligrams, we just need to times 10 to the power 3 again. So it shows you 10 to the power 6 milligrams per liter. So we can say that's a 10 to the power 6 ppm as well too. Instead of writing the milligram per liter, we sometimes use that we kind of mix use the ppm. By the way, that unit ppm you will see that again in year 12. And you won't get these conversion in your formula sheet. So then this is something that you must memorize. So copy this down on the ppm, milligrams per kilogram, milligrams per liter. So kilograms, basically I'm talking about in the 1 liter of the water too. Okay, next one we have parts per billion. Then what about the parts per billion? Okay, parts pp parts per billion. We don't use the quite common. So ppb is known as micrograms per liter, which is equivalent to 10 to the power minus 6 grams per liter too. Okay, so in case we have 10 to the power 6 ppm, which is a concentration of this solution here, now we can clearly see this is more concentrated, less concentrated there by looking at the color. Yep. So, which means we can find that in ppb. So example, we have 10 to the power 6 ppm will be equivalent to then 10 to the power 9 ppb, which is a parts per billion. So we commonly use the unit ppm, ppb in when we're talking about molecular biology. Say like we have how many like micro stuff, the germs we have in per centimeter, per grams and stuff. Okay, we also have some percentage value here. Okay, I would like you to focus on these weight per weight, volume per volume, weight per volume. So we can have different percentage volumes like that. So weight per weight, W for weight means the weight per weight. Oh. It simply means grams per gram. So that's same as percentage in grams per gram. For 100 grams, grams in 100 grams, you should say. Okay, volume would be like this. Percentage in, say, milliliter in 100 milliliter. And weight per volume would be percentage in grams per 100 milliliter there. So let's see some of the example for that is, okay, we have, let's say we have, for the question 3.1, let's go through some of the questions there. What is the concentration of the in gram per liter of a solution containing 8 grams of sodium chloride in 500 milliliters of solution? So we have 3.1. Then we can find the grams. So what we given is 8 grams per the 500 milliliter. What we want to change that into is we want to change that form of the gram per liter form. So leave the grams on the top, but change that milliliter into the liter. So 500 milliliter in the liter means 0.5. As a 1 liter is 1,000 milliliter. Then you to get times 2 of that, you get 40. Oh, actually 16 grams per liter. Okay, and follow the sig fix we have. We have a 3 sig fix, 8.00. So 6.0 in grams per liter is the full answer for 3.1 we have. Now let's do the 3.2. The next, same question, 3.1. What is the concentration in gram per liter of the solution containing 5 grams of glucose and 250 mils of glucose? So we have 5 grams, 5.00 grams divided by 250 mils, which is same as 5 on 0.25 liter. Giving you out 5 divided by 0.25 times 4 to 20. Check the sig fix. We have a 3 sig fix again, so 20.0 grams per liter with the final answer. Okay, next one. Saturated solution of the calcium carbonate was found to contain 0.0198 grams of calcium carbonate dissolved in 2,000 grams of solution. Calculate the concentration of the calcium carbonate in solution in the parts per million. Okay, let's do that. So what we are given is, we are given 0.0198 grams of the solute, which is calcium carbonate, into the solvent, which is 2,000 grams of solvent here. Okay, ppm again, it stands for the milligrams per liter. So we cannot just change that liter into the kilogram sometimes, because as you probably learned in the mathematics times, 1 kg of the water is equivalent to the 1 liter. Yep. So using that, what we have to do is change the unit gram into kg, the kilogram. So 2,000 grams is equivalent to 2.0 kilograms. Divided by, now grams into the microgram. And what we know about the microgram is, milligram is 10 to the power minus 3. Okay, so we have this much of the grams, the times that 1,000. So giving you 1,000 there, 0.1, so 1, 2, 1, 2, 3. So we get 19.8 milligrams in that case. Then you get the unit of ppm, as we have this, 19.8 divided by 2, you get 9.9. Again, the sig fix is given as 3 sig fix, so you must match that to 9.90, 3 sig fix, ppm, which is this is equivalent to the parts per million. All right. Okay, let's do the next one too. We have 0.0537 grams of sodium chloride per the 250 grams of solution. Now found in the parts per million again. So what we have, 0.0537 grams of the sodium chloride divided by, we have 250 grams of solution. Okay, first convert the grams on the top into the milligrams. So how do we times by times 1,000? So 1, 2, 3. So we have 53.7 milligrams on the top. Divided by 250 grams in the kg, that would be 0.250 kg, or the liter. Again, 1 kg of the water is same as 1 liter. So we can kind of mix use a liter and the kg over here. So 53.7 divided by 0.25, just make it times 4, 214.8. Now, fix that into the given sig fix. We have, how many sig fix we have? We have 4 sig fix and 3 sig fix. So it's tend to say like a 3 sig fix in that case is approximately same as 215 ppm in 3 sig fix. That's the final answer. Okay, so unit conversion will be very common from now. Okay, I want you to try yourself for those questions in the back over here. Some of these questions, give you about 10 minutes. Caramel. Fish and everything. Okay, just take a rest. 5 minutes. 시간 되는 대로 저기까지만 하면 될 것 같아 오늘은. 이렇게 보냈는데 지금 이게 인터넷이 지금. 응?
어디까지 해야 돼?
타. Hi John. Okay, let's see from the first one. 750 mils, a bottle of the whiskey contains 244 mils of the ethanol. What is the concentration of the ethanol in percentage, volume per volume? So what we want to get from here is we want to get the milliliters per 100 milliliters. So the way you can show that is, so concentration of the ethanol can be shown as, we have a 244 milliliter on that 750 milliliter here, okay? It's not really giving the percentage value, so what you can do is times the 100% to get the percentage wise. Then you should get 32.5%. Make sure, but in your unit, put that volume for volume. Because by saying the percentage here, it can be meaning of the weight per weight, weight per volume, volume per volume. So you need to specify what percentage you have. This is very important, because you actually lose a mark by not writing by not writing this. Yes. Next one, the concentration of ethanol is at 350 ml. On the bottle of the beer is a 4.9%. The volume of the ethanol in the bottle. So what we can do is, given that concentration of the ethanol is given as 4.9% volume per volume, which means indicating what? That per 100 mils of the ethanol, there will be 4.9 milliliter of the ethanol will be 100 mils of beer, 4.9 milliliter of the ethanol will be present. So what we do, we bring up the volume of the beer. So to get the quantity, so we can do 4.9% times that to 350 will give you out the volume. So what we know about 4.9 is 4.9 milliliter on 100 milliliter times that to 350. Okay? Because 4.9% means that we have that much of the ethanol in that much of the beer, 100 mils of beer. So do so, 4.9 divided by 1,000, or just simply 350 times 4.9. You get 17.15 milliliter of the ethanol in that case. Okay, but fix that into the given sig fix we have given 2 sig fix. So that is approximately same as 17 milliliter in 2 sig fix. That's counted. So the calculation itself is pretty simple. As you know, like you probably practiced that before in your math times, but sig fix is very important what you have to follow. Next one, calculate the concentration of the following solution in the ppm. So 25 milligrams of calcium chloride dissolved in the 5 kg of the solution. So we're given the ppm. Concentration of calcium chloride can be found by milligram, 25 milligrams divided by 5.0 kg. Beautifully given the milligram per kg, which is the ppm. Saley, what'd you get? Hmm? What are you looking at Hannah's for? what did you get? You should get 5.0 ppm in 2 sig figs. That's the answer for A. B. 1.25 grams of lead nitrate dissolved in the solution. Again, we need to find that into of the 2,000 grams. Convert that into the unit of the milligrams per kilogram again. So grams for that. 1.25 times 10 to the power of 3. This is how you change the milligrams. Grams into kg would be 2.0 kg. If you found it correctly, you should get 625 ppm. Given that we have a 3 sig figs followed then the 3 sig figs as well. C. Magnesium sulfate dissolved in that 150. So we're given 4.0 times 10 to the power minus 3 grams of the magnesium sulfate dissolved in 150 grams. All right, convert that into 10 to the minus 3 grams itself is already tell you that this is a 4.0 milligrams. Okay, then divided by 150 grams in kg is 0.150. Then you must get the final value of the 27 ppm again. Next one, the nutrition panel of the flavored milk drinks states that it contains 35 grams of sugar and 7.5 grams of fat in every 250 mils of serving. What are the concentrations of the sugar and the fat expressed as the percentage weight per weight? So what you have to do for the sugar, first of all, we have that 35.0 grams per given that 250 milliliter. So you divide these two first because we are given unit of the gram per milliliter and then times 100%. You get the percentage value. Okay, then therefore, okay. Hannah, what you get for the sugar? 14 in how many sig figs? 2 or 3? We can fix in 2, but also in 3. In case we ever use a 35 with the 3 sig figs on the top here, okay, we need to follow that 3 sig fig, which is 14.0 grams percentage, which is weight per volume here again too for the units. Okay, follow the unit they're asked in here, so don't miss that weight per volume. That's again counted. Next one, we have given fat. Fat is contents of the fat is 7.5 grams per 250 ml. Notice that we have a 2 sig fig value on the top. So times 100%, you would get 3.0% in weight per volume as well. Okay, next one. CHEM toxin is a dangerous toxin that is found in some fish in Australian tropical water. So the amount of this chemical that can kill is a 70 kilo human is approximately 50 milligrams. What is a lethal concentration of toxin in the human body in parts per billion? So what's a parts per billion, Joanne? ppb is known as the micrograms per kg we have. So that's same as 10 to the power minus 6 grams per the kg, which is written on the other side of the board there too. We're given that the amount of this chemical is approximately 50 milligrams. So we're given 15 milligrams of the toxin in the 70 kg of the human. Or that's actually killing the person with 70 kilograms of weight. So what we need to do, we need to convert the milligrams into the grams or the micrograms. So milligrams and micrograms is that milligrams to the micrograms will be 15 times 10 to the power minus 3 microgram divided by 70 kg. Leave that. Then you get 2.1 in 2 sig figs times 10 to the power of the 2 ppb, or 210 basically. Next one, fluorine is added to the toothpaste in the form of the sodium fluoride. The permissible level of the fluorine in the toothpaste is 0.22% weight per weight. 175 grams of toothpaste tube contain 0.42 grams of the fluorine. calculate the fluoride concentration percentage weight per weight to see if it is above or below the legal level. So you need to assess it. This is a kind of common question you will find in year 12 later on too. You're asked to find the percentage in the concentration value, compare that. Okay, so 175 means we have 175 grams on that given, the 0.42 grams of the fluoride we have in the 175 grams of toothpaste. Okay, let's find that in terms of the percentage there. So 0.42 divided by 175 times 100, you get 0.24% weight per weight. Compare that to what we have. Legal value. The legal permissible value is 0.22. So as 0.24% is greater than 0.22%, it is more above the legal value, legal level. That's the final answer. All right, finished up to here. Okay, again, these units will not be given in your formula sheet. They will not tell you, but they will give you the questions like they're here. So try to understand that as ppm is milligram per liter, ppb, and weight per weight. Excuse me. Okay, weight per weight, weight per volume, weight per volume. You will see that those again in year 12. Okay, and the hardest question you can get is you get a unit conversion. Okay, move on to the next page. We're going to learn about something called then molar concentration. This is the most common unit of the concentration we use in chemistry. Okay, first of all, don't leave that what the meaning of the moles. Okay, moles. Ben, what do you mean by the 1 mole again? 23, 22, 23. Yeah, that's Avogadro's number. So having a 1 mole of something means we have that many of that too. So atoms, we are counting in number of moles, not in the terms of like couple dozens, because too many of that in the given, even in the 1 liter water. So when we find the concentration, and this will kind of bothering you from now, we are finding concentration in the unit of mole per liter, which means that it's given over here, it's mole per liter. So saying 1.0 mole per liter means that we have 1 mole in 1.0 liter of that water, of that solution probably. Okay, so simple as that. Saying we can have the various number of the mole per liter. So what we see from there is, as we can see on the page, what's the page number? The page 79. Concentration moles can be found in the amount of solute in moles divided by the liter. So as we learned this, the formula of the N equals to M over MM, this is another formula that you need to memorize too. That concentration is N over V, where N is simply be what? The number of the moles. Okay, V is simply be what? The volume of the solvent. Therefore, you can get the concentration as well, just like a gram per liter. Just like a gram per liter. And spoiler, the common question you get from now is, from here, you will ask to convert that into there. Yes, from ppm, from the ppm, you will be asked to convert it into the mole per liter, or vice versa, from mole per liter to ppm. And that's the trickiest part of today's lesson, basically. Okay, let's see how to find. So let's do some mole per liter concentration calculation for in that 3.2 first. I'll show you how to do this. It's actually pretty easy questions. So calculate the molar concentration of the solution that contains 0.105. Okay, question 1. Now, when the question is specifically asking you to find molar concentration, this is a very special symbol that you can use. Okay, leave that. Okay, guys, I want to look at the board first. This is something that you need to copy down. When you are asked to find the molar concentration, here, this is all the concentration. We never wrote in the concentration unit. But when you're given the questions like molar concentration, you can write that the big bracket, the square bracket like this, showing that potassium nitrate inside, that's known as the molar concentration symbol. Of the potassium nitrate like that too. These, I could not write it on this big bracket. Instead, if I want to say that, I can write a C of something, showing the concentration of something in here, which is different to the molar concentration. There's a very special unit, which is a symbol we use only for the molar concentration. Okay, so what we know about this is that C is equals to N over V, so N over V, make sure you show that working out. The formula here again too. It's given as we are given 0.105 mole on that 200 mils of solution. How to convert into unit of the mole per liter? We leave that one we have on the top, which is mole, divided by 0.2 liter like this. Then you to get 0.525 mole per liter like this. In some of the textbook or some of the school teachers probably using the unit of this like this too. Big M. That's giving you the molar concentration unit. It's actually commonly used in the university, but in the HAC standard in year 11 and 12, we try not to use that big M. We can, okay, but we prefer to show that mole per liter in terms of the your concentration unit. But if you see that in some textbooks, it could be the old textbooks, yes, that means that mole per liter again. So these two are basically the same. Okay, let's do the next one then. We have 0.24 mole of the glucose dissolved. So what we do is show the symbol, glucose, or you can remember that C6H12O6 is a glucose, is equals to, we have 0.24 mole divided by 500 milliliter. That's equals to 0.24 divided by 0.5 mole per liter there, giving you 0.48 mole per liter straight away. Okay? Now, next one, question 3. Calculate the amount in moles of ammonia in 25 mils of the 0.3277 mole per liter ammonia solution. Now, this time you're not asked to find the concentration. Instead, you're asked to find the amount of moles. Question 3. That's question 2. How do you find the amount of moles? So we bring up the formula here that C is equals to N over V. We can slightly modify the equation, the formula into like this. Then N must be CV. Just like what we've known about the N over in the chapter 2, the N equals to M over MM. There's another formula we can use to determine the number of moles. Make sense? Okay. So what you need to show there is as C is equals to NV. Oh, sorry, N is equal to CV. Okay. So N of V, what we found in here is ammonia, NH3. It's good to show that what we are looking for, what you're finding for. Okay. Times that. Concentration given, see that is a molar concentration 0.3277 times that 25 mils means make sure you convert that into the liter. If you give a milliliter, it means you need to convert that by how 25 milliliter times 10 to the power minus 3, or you can just simply say 0.025, doesn't really matter. Okay, if you don't convert that, you will get a completely different answer. Then you will get this. That's not right. 0.3277 times that 25 times 10 to the power minus 3. You must get 0.081925. Don't leave your answer like this. What you do, you can use a scientific notation. That's 1 point. Given that sig fig, we have 4 and 3. If you're multiplying the 4 and 3, you're following the lower sig fig value, which is 3 in this time. So it'll be 8.19 times 10 to the power minus 3 mole. Again, when you're multiplying two sig fig values, which is 3 and 4, you follow the smaller sig figs. Okay, Okay, try the next one, question 4. I give you about 2 minutes to try this now. The question 4. So, So remember, you need to fix your answer to the given sig fig. We have our 3 sig figs given here. So, and that's kind of 1 or 2, that could be considered to be 1 sig fig. So in that case, we follow the 3 sig figs. We don't really fix your answer to 1 sig fig value because we don't really use 1 sig fig at all. So times that, you get 0.025. So that'll be 2.50 times 10 to the power of the minus 3. Okay, mole. It's given. Easy. But here, I can go another level here, the further level. Yes, I can, really, I can. I want you to find the mass of this. They can ask you like, hey, find the mass of the, then to make the concentration, how much mass, what the mass of the grams. And what we do, we put that, m equals to km m4 is equals to n times the molar mass. That's how we mix that, something you learned in chapter 2 to chapter 3. Okay, so how we do? N is given as 2.50 times 10 to the power minus 3 is given. Using your periodic tables, make sure you show all the relevant things you have in the potassium permanganate. Potassium is 39.10 plus that permanganate, manganese. Excuse me, okay. Mn is 54.94 plus that for oxygen, 4 times 16. That's included in your working out. So 39.10 plus 54.94 plus 4 times 16 times the 2.5 and 10 to the power minus 3. You'd get 0.3951. Again, to fix that into given sig fig, which is 3, that's approximately 0.395 grams. That is the kind of questions that you can face as well too. That's what I mean, like what is shown in the in-class exercise 3.3 here as well too. Okay, so I want you to try the questions on your page 82, question 1 and 2, in-class exercise 3.3. Think about how you're going to use that n equals to m over molar mass and also n equals to CV and mix use those.
we talk like a minute?
Let's go question 1. Calculate the concentration in mole per liter of the solution that contains 16.8 milligrams of silver nitrate dissolved in 150 mils of solution. So we are given, so I want you to follow my working as writing on writing on the board here, because you need to write every single point of here. So first, start with what we have given, the mass of the silver nitrate. I just copy that what we have given. It's 16.8 milligrams. Now, in terms of this, grams, because we need to find the grams to find in the number of moles, that'll be, you can just simply use 6.8 times 10 to the power 3 grams like this here. Or we can say 0.0168, doesn't really matter, but that's the less risk to make a mistake. All right, then we need to find the N, which is silver nitrate. This is how we not make the mistake. Again, N equals to M over molar mass, which will be given as 16.8 times 10 to the power 3 divided by molar mass of silver nitrate. So counting all that components we have, started from silver, which is 107.9, plus then nitrogen, 14.01, plus the 16 times 3, like this. Okay. So 107.9 plus 14.01 plus 16.3 and 16.8 divided times 10 to the power 3 divided by that, you get 98.88 mole of the given. No, I'm sorry. It should be 10 to the power minus 3. It's my bad, sorry. It should be less than that. No wonder the value was so big. Okay, not the 99, so you should get 9.8. 8 times 10, 9.89 actually, 9.89 times 10 to the power of minus 5 mole given. All right, from here, as we need to find the concentration mole per liter, the concentration, this is a symbol you must use, the concentration of the silver nitrate. Yes, you can use C, the concentration, for the general concentration formulas, but prefer to show in the molar concentration value like this. Make sure you show the N over V in your working out. That's important. So 9.89 times 10 to the power minus 5 divided by the volume we have, which is 150 mils, or 0.15, straight to the liter. So what you can do is say, from the value saved on your calculator, divide that by 0.15. That's simply what you can do if you have your calculator with you. Then 6 point, given the sig fig, we have a 3 sig fig, so fix that into 6.59, which is a 3 sig fig value, times the 10 to the power minus 4 mole per liter. This is the final answer for question 1. All right, question 2. Calculate the concentration mole per liter of the solution that contains 4,000 milligrams of ethanoic acid dissolved in 100 mils of solution. So we are given that mass of the ethanoic acid, CH3, COOH, is given as 4,000 milligrams. Now in grams, easy, that would be 4 grams simply. Then N is equals to M over molar mass, that's 4 divided by 2 carbons plus that 2, 4 hydrogen, or 8, plus the 2 oxygen. So you get 2 times 12.01 plus 4 times 1.08 plus 2 times 16, and 4 divided by that, you get 0.0666 mole for that ethanoic acid. Good. Next step, concentration of the ethanoic acid is N over V, therefore 0.0666 divided by, given that 100 mils, which is 0.1. Then you get 0.66. How many sig figs we have? We have 3. It doesn't really tell you, so let's leave it the 3 sig figs. 6 mole per liter for the final answer. How'd you go with the question 3? The Okay, start from here. Find the mass of the sodium chloride required. So we actually need to make some solution with this, like salt water. And we want to make in the concentration of the 1 ppm. Then how many of these salt required in grams to make that 1 ppm? So start from 1 ppm here. 1.0 ppm is same as what? 1 milligrams per 1 liter of the water. Okay, or I can simply write that as in terms of grams, that's same as 10 to the power minus 3 grams on 1000 milliliter as well. Or say the 1 liter, that's the same thing. Okay, you don't need to show the conversion of the liter to milliliter here. Now, what we give, that means that for this, we need to have the certain grams, 400 milliliter of the solution. Then, as we only have 100 milliliter, what we can do is the mass of the sodium chloride required, NaCl required would be same concentration times that the volume. In that case of the mass, this is not the n, by the way, because we only have the grams on the top. So what is this? We have 10 to the power minus 3 grams per 1000 milliliter times the 200 milliliter of the solution we have. Cancel out 100 and that, you're giving you 10 out. Then you get 10 to the power minus 4 grams of the sodium chloride is required. Does it make sense? Okay. Now I can ask you to, like, and then what would be number of moles inside of that too? Just simply use n equals to m over mm in that case. There's another kind of question you can face. So you can think about, hey, to find the mass from here, you're given that. So this is something that you need to understand about the concentration. Again, concentration means that how much solute dissolve in the how much of the volume of the water, like in here. Does it make sense to you? Yep. Pardon? I can't hear.
Why is it
N? Okay, because we're looking for the mass of that, and we're only given the concentration in unit of the gram per liter. Does it make sense? Okay, it's not like a part of formula that you don't try to memorize it in terms of the n equals to CV here. What I'm trying to say here is the concentration unit, you're saying that is the gram per milliliter. So simply thinking this way, if the concentration is this, okay, if I'm taking the 100 mils out of that, how much of solute will there be inside the 100 mils? So the same question as, I have this 100 mils of this, okay? If I'm taking, they say, like a 10 mils of that, assume that it's a 10 grams dissolved inside of here, and 100 mils of solution given in here. If I'm taking 10 mils out, what would be the grams of solute dissolved in here? I'm taking from 10 mils. Not making sense? Okay. Show it again. In that solution I have here, I have 100 mils. Okay, that has the 10 grams of the solute dissolved. So assume that all the solutes are dissolved and they kind of distributed uniformly here. Then I'm taking that 10 mils liter from the 100 mils. Then how much of the solute do you expect to get from the 10 milliliter? It'll be 1 gram. Because it follows the ratio values over here too. What I try to say here is 1 ppm simply be 10 to the minus 3 grams per 1000 milliliter. And I'm taking the 100 mils. Does it make sense? Means the amount of the solute I require for that is 10 to the minus 4, used following the ratio value. Does it make sense? Okay?
For the same question,
Yep.
can I just say like let the mass in milligrams of sodium chloride from X and then do it like the math.
Oh, X. Yeah, you can.
And then just like not convert the milligrams to grams, and I just do it in milligrams.
You leave that answer in milligrams.
Yeah, and then I convert the 100 mils to like liters.
You can, but leave your answer to the standard unit, which is grams, if you can. Unless the questions ask you to find the specific milligrams. Okay? The answer's right, but it's a little bit risky. Good. Ellie.
Yes, sir.
Okay, 20 more minutes.
Uh,
Okay? All right, next one. So again, here, I'm going to bring up here, inside of this 100 mils of water. I know. Yeah, okay, 20 minutes. Okay, 100 mils of the solution I have in here, say that we have a 10 gram solute. So you see the vitamin C kind of dissolve inside in here. So what I'm doing is, I'm kind of putting extra water there, like this. So making it up to say like this, approximately there 150 mils. Okay, so from there, now I made 100 mils to now 150 milliliter in there by adding the 50 milliliter of the H2O. That's what I just have done in here. Hannah, I kind of, this is called a dilution, yeah? I diluted that solution, but did I change the amount to dissolve in the solution here? So how much of the solute will I get in here? If we start from here, diluted, then how much? Huh? I had 10 grams solute dissolved in the 100 mils before, okay? And then I put the extra 50 mils onto that solution, just like you saw in here. Then how much of solute was dissolved? It will be dissolved in here again. Hmm? 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 Okay, guys, did I add extra solute? Did I add extra tablets there? No, I just add water. Yeah, it'll be 10. Just like here. If I drink this, I'm drinking the same amount of I will not drink it, by the way. Okay, I'm drinking the same amount of the vitamin C, which was more concentrated before. So can I say this solution here is more concentrated? Because in the smaller volume, we have the same amount. It is more diluted. You okay, Hannah? Make sense to you? It's actually shown on your page on the 3.3, page 85 here as well too. Before and after, just exactly same as what I showed in here. Even though I increased the volume of the water by putting extra water there, we didn't change the amount that dissolved in that water, in that solution. Now, how about I change that to this? If I had, say, 1 mole was dissolved in that, okay, after dilution here, it will still be 1 mole. Okay, then how do you find the moles? We found that N is known as the what? C times the volume. Okay, so assume that this is I'm trying to find N1 and N2 separately. Then what I do for the N1 here is, using the N equals CV, N1 can be found by the C concentration of the solution 1 times the V1, the constant volume of this. Which is same in here. N2 would be C1 and V2, C2 and V2. Where the C2 stands for the concentration, new concentration of this diluted solution, times the new volume, which is 150 mils in that case. Make sense? Okay. Shall we do that? We can do. What we do means that the concentration giving you 0.1 mole per liter in that case. That's giving you what's 1 divided by 1.5. You get 1 divided by, my bad, that's 10 mole per liter in that case. That's giving you 6.67 mole per liter here. Even though we have a different concentration here, okay, but remember that we have a same amount of mole dissolved. The only difference here and there is the volume that are added extra. So combining these two, then can I say the N1 is actually equals to N2 because we did not change the amount of mole dissolved. We just added some extra water. Then can I say the N1, which is founded by C1V1, is equals to C2V2 like here too? Does it make sense too? Okay, that's the new formula that you can use in case only for the dilution. Dilution. Dilution formula in that case. Again, dilution means that we just put the extra water, or sometimes we just kind of evaporate some water. Yeah, so you're thinking about again when something is not really like a blend, you kind of give some more heat and then make it more salty. All right, that same, but you still have the same amount of salt or sugar dissolved in there. We're not putting extra salt and sugar, but we only put the extra or the less of the water, which is solvent in that case. So let's have a look at some questions related to that again. Question 1. Calculate the concentration the solution formed when 10 mils of the water is added to 5 mils of the 1.2 mole per hydrochloric acid. Okay, I want you to look at the board first and show you how to do the question 1. What you have to realize there is there's a 10 mils of water is added. Extra water is added. It's not the final volume. So I want you to determine from here that C1 and V1 first. The initial concentration. So initial concentration we're given is 1.2 mole per liter. Initial volume we're given as 5 milliliter. Okay, so let's change that to the liter form too. That's 5.0 times 10 to the power minus 3 liter then. Does it make sense? Okay. Now let's talk about the final volume. Remember that we added extra 10 mils on the top of the 5 mils. So final volume would be 5 plus 10 milliliter, isn't it? Which is 15 milliliter. That's the same as 15 times 10 to the power minus 3 liter there. Then what I do is, remember that you diluting something means that you don't change the number of the moles. You don't change the number of moles. You just put the extra water. That's it. So you will still have the same amount of the vitamin C in here, same as that. So I'm bringing up the formula that C1V1 is equals to C2V2. But the question is asking you the new concentration. That C2 can be found by C1V1 divided by V2 in that method. Then C1 we're given 1.2, substituting the value 5.0 times 10 to the power minus 3 for the V1 divided by 15 times 10 to the minus 3. And you will realize that these two will be cancelled out. Okay, so you don't really need to change the liter to milliliters in that case because the ratio values, but you can also. There's nothing wrong to showing it that. Then you would get 1.2 times 5 divided by 15. Oh. You must get 0.4, given that 3 specific, 2 specific, 0.4 mole per liter in the 2 specific values. Again, try to remember or understand about what you mean by dilution. You are putting just extra water. And be careful with what's given here. Sometimes the question giving you that final volume is this. Or the question can giving you the questions like, hey, we added extra 10 mils on that. So that means you get the different volumes, the final volumes in that case. Okay, question 2. Calculate the concentration solution form when 95 mils of water is added. Again, it's added to the 5 mils of the 0.5 sulfuric acid. So we're given, question 2, given that C1 is given as what, 0.500 mole per liter. V1 is initial volume is given 5.00 milliliter there. Okay, V2 we're given 5 plus 95. So I just convert that into liter, so I don't want to confuse you. That's 100 milliliter. Which is same as 10 to the power minus 3 liter in that case. Okay, again, use the C1V1, or you can show that C2 is straight to C1V1 was V2. That's okay. But make sure you show the relevant formula. Otherwise, I don't know where you get these values from. C2 then equals to 0.5 times the V1, which is 5.00 times 10 to the power minus 3, divided by 100 times 10 to the power minus 3 as well. Cancel these two out. Then you get 0.5 times 5 divided by 100. You get 0.025. Given the sig figs value, we have a 3 sig figs. So fix that into 0.250, which is a 3 sig fig value. Okay, mole per liter and 3 sig fig. That's it. Okay. Okay. Could you try for the next two questions then? Question 1 and 2. See, this is where you get the ppms from now. We just got to go up to here then. It's not actually dilution questions we have, but no? Yes? All right, question 1. We have the 0.002 molar of this sodium chloride. Let's convert that into the ppm. So it's kind of unit conversion again from the mole per liter to ppm. So it's nothing to do with dilution. Okay, interesting. Okay, we're given the concentration of sodium chloride, which is this 0.002 mole per liter. So what we have to do is we need to convert the moles into the grams. So m is equals to n times the molar mass. That's what you need to do. The mass of the sodium chloride we can find in the given moles given in here per liter. It would be 0.002 times that 2 molar mass of the sodium chloride, which is 22.99 plus 35.45. Okay, so showing that 22.99 plus 35.45 and times answer times that 0.002, you get 0.1169 grams. All right, that means that this much grams from the moles we have in the 1 liter. Kind of makes sense, okay? Just simple unit conversion here. Now, this is what? That times we want to convert that into milligrams. How do we do that? Grams per milligrams? Just simply that times that 1,000. And you get 116.88 milligrams in that case. Therefore, that 0.00200 mole per liter is equivalent to 116.88 milligrams per liter as well. Which is what? In the given sig fig we have a 3, so that's fixed it to 117 ppm in that case. Kind of makes sense? Okay, let's do question 2 again. Same. We have a sodium hydroxide this time, so given that sodium hydroxide molar concentration is 0.0100 mole per liter given there, and we need to convert into ppm. So as, again, same method, m is equals to n times the molar mass. The mass of sodium hydroxide is found by 0.01 times the sodium, 22.99 plus 16 plus 1.08. So 22.99 plus 16 plus 1.08. That times the 0.01, you get 0.3999. So that's approximately 0.400 mole grams. I'm sorry. Okay, which is same as what? That's 400 milligrams in that case. Therefore, same unit, 0.0100 mole per liter of that solution is same as 400 milligrams per liter, which is 400 ppm. That's the final answer. Again, you won't be told about ppm value here yet. Oh, one more question. Sorry, we have 5 more minutes. Yeah. Sorry, my bad. Just one more. Just one more. Okay. ppm, they will not tell you what the ppm stands for, so you need to remember that's milligram per liter. Okay, from your try yourself question here, could you do question 3? Thank you. Ben, could you pass one each? Thank you. Let's do a prac next week. Okay, for to do the question 3 like here, so what volume of the 10 mils of the hydrochloric acid would be required to prepare 250 mils of the 0.3 molar hydrochloric acid HCl solution? So, started with the writing all the relevant information we have. We're given that initial concentration, we have 10 moles per liter. Okay, we want to make that diluted into 0.3 mole per liter here. And then we want to make the solution that has 250 mils. Okay, then use that C1V1 equals to C2V2 over here. You can find the V2 from there is actually same as what? C1V1 divided by C2 as well. Okay, substituting the relevant values, we have 10 moles. Convert that into 0.25 liter. It's good to show that. C1, we have, oh, I'm sorry, V1, I must say. V1 is equals to C2V2 divided by C1. It should be it. So 0.3 times that 0.25 divided by C1, which is 10. Okay, so if you calculate it correctly, 0.3 times 0.25 divided by 10, you should get 0.0075 liter. So in terms of that, it's given as answer D. Yes? It's good too, yeah. For this kind of case, yes, you do, because you need to show in the unit of the liters. If you chose to do the milliliter, you get the unit of the milliliter at the end. And sometimes they confuse you. This is why, this is why I said I don't want to confuse you about that, changing the units. Okay?